So, if you think about an offshore well, the Christmas tree at the surface is your primary control system, right? And the blowout preventer, well, that's your emergency control system. But what we're looking at in this explainer is the absolute last resort. We are talking about the ultimate rock-solid failsafe that kicks in when literally everything else has gone wrong. It's called the Surface Controlled Subsurface Safety Valve, or SCSSV for short. But before we get into the nuts and bolts of how it works, I want you to imagine a truly terrifying scenario. Just think about the unthinkable for a second. What happens if a massive cargo ship collides head-on with an offshore platform? Or what if there's a catastrophic structural failure, or even a massive explosion that completely obliterates all the surface infrastructure? When that Christmas tree is gone and the surface control systems are totally wiped out, what exactly stops that high-pressure reservoir from unleashing a massive, unstoppable blowout straight into the ocean? Well, the answer is a hidden savior. You see, the ultimate emergency brakes for these wells, they don't sit on the platform, and they don't even sit on the ocean floor. They are safely located way down, about 60 to 90 meters, so roughly 200 to 300 feet, beneath the mudline itself. And because they're buried so incredibly deep below the seabed, they're completely protected from basically any surface disaster, whether that's a dropped object, a massive anchor dragging across the seafloor, or an explosion up top. This valve is out of harm's way. Okay, so here's our roadmap for this explainer. We'll start with Section 1, the ultimate offshore failsafe. 2, the failsafe closed principle. 3, forging the indestructible flapper. 4, installation and retrieval methods. And finally, Section 5, mandatory testing and safety. Okay, let's dive into this with Section 1, the ultimate offshore failsafe. To really get why the SCSV is so effective, we have to look at exactly where it lives inside the architecture of a completed well. Notice the sheer scale of the protection here. You've got the seabed right at the top. Now, travel down with me past the mudline suspension system, down past that massive 30-inch structural conductor casing, and deep into the production tubing. Right there, that's where the safety valve lives. By placing this critical barrier 60 to 90 meters down the hole, engineers have essentially completely isolated the well's shutoff mechanism from the chaotic environment of the open ocean. So if everything at the surface is just violently sheared off, this valve remains perfectly intact, resting completely silently in the rock. Moving on to Section 2, the fail-safe closed principle. So you're probably wondering, how does it actually know when to close if all the surface controls are destroyed? Well, it all comes down to a really brilliant mechanical philosophy called the fail-safe closed principle. And this simply means the valve requires active, continuous energy just to stay open. Looking at this cutaway, you can see exactly how it works. Inside the valve body, there is a super powerful coiled spring. Left entirely to its own devices, that spring pushes up and forces a hinged metal plate, which we call a flapper, tightly against its seat, completely closing the well. Now, to actually get oil or gas to flow during normal operations, the platform pumps hydraulic fluid down a tiny control line from the Christmas tree at the surface. This fluid applies an intense pressure, we're talking 150 to 250 bar, against a piston and a flow tube. That compresses the heavy spring and physically pushes the flopper open. And as long as that hydraulic pressure is perfectly maintained, the well produces. But let's go right back to our disaster scenario. Imagine in a split second, total disaster stripes the surface. The Christmas tree is violently sheared off. That hydraulic control line running down into the well is instantly severed. What happens in that exact, precise millisecond? It triggers an immediate automatic chain reaction. Step 1. Because that line is cut, the hydraulic pressure instantly drops to absolute zero. Step 2. With nothing holding it back anymore, that massive torsion spring immediately releases all its stored energy. Step 3. The flow tube retracts and the flapper violently slams shut against its tapered seat. In Step 4, the well is completely sealed. There's no electronics involved, no human intervention, no computer signals trying to route through a broken cable. It is just pure, undeniable physics instantaneously isolating the ocean from a massive hydrocarbon reservoir. Which brings us to Section 3, forging the indestructible flapper. Of course, for physics to actually do its job here, the materials have to be completely flawless. This flapper is a single point of failure in the absolute truest sense of the word. If it breaks, or bends, or corrodes, the failsafe fails, and obviously that is just not an option. When that flapper slams shut, it might suddenly have to hold back the full, terrifying force of the wellbore pressure. In high-pressure wells, that can reach anywhere from 500 to 700 bar. To put that into perspective for a second, 700 bar is roughly 10,000 pounds per square inch of pressure, constantly trying to force its way past a single, flat metal hinge. The job requirements for this tiny piece of metal are literally brutal. Think about it. It has to open freely against a heavy spring force every single time the well starts up. It absolutely must close in a fraction of a second the moment pressure drops. It has to perfectly, flawlessly seal against that 700 bar we just talked about, and honestly, perhaps most impressively, it has to survive just sitting there in a stream of erosive, high-velocity, and highly corrosive produced fluids for years on end without degrading even a little bit. To pull this off, engineers don't just use standard steel. High-quality SCSSV flappers are crafted from aerospace-grade nickel alloys or cobalt-based alloys. This gives them extreme hardness and total corrosion resistance. All right, Section 4, Installation and Retrieval Methods. So even an indestructible aerospace-grade failsafe occasionally needs some maintenance or even a replacement over a 25 to 30-year well lifespan. So how do you fix a valve that's buried nearly 100 meters below the ocean floor? Well, the crucial point is that operators have to make a major engineering trade-off right during the well completion phase. They generally choose between two main designs. The first is a wireline retrievable valve. This one is lowered down and latched into a specially machined landing nipple inside the tubing, locked in place with a snap latch. It's vastly easier and cheaper to retrieve because you just use standard wireline tools pulled directly through the open bore of the tree. But because it sits inside the tubing, it restricts the diameter and actually chokes the overall production flow. On the flip side, you have the tubing retrievable valve. This one is actually screwed in as a physical joint of the production tubing itself. Now, this maximizes the well's flow, which is great, but if the valve fails, the operator has to pull the entire production tubing string out of the well. And let me tell you, that is a massive, incredibly costly operation. And finally, Section 5, Mandatory Testing and Safety. Because these valves really are the ultimate barrier protecting our oceans, we don't just install them and cross our fingers hoping they work. There is a very rigid, mandatory framework of protocols and regulations to make sure this mechanical hero is always ready to act. Regulators require operators to literally simulate a disaster on a regular basis. Typically, every 6 to 12 months, operators have to perform a really strict test. They intentionally bleed that surface hydraulic control line pressure all the way down to zero. Then, they confirm exactly how long it takes for the valve to close, making sure it happens within a required time limit. After that, they depressurize the tubing above the closed valve, apply pressure from below, and carefully watch the gauges to confirm the valve is holding a perfect seal. Only if it holds is the well certified as safe. If the valve doesn't close on time, or if it leaks even slightly, it is classified as a direct, immediate threat to well integrity. Operations halt right then and there, and it must be repaired or replaced immediately. Regulators absolutely do not mess around with this, and history proves exactly why. During the tragic Piper Alpha disaster in 1988, where a catastrophic fire and explosion totally destroyed the platform, the SCSVs were put to the ultimate, terrifying test. The mudline safety valves on all 36 wells successfully shut in. They did exactly what they were engineered to do, flawlessly sealing the reservoirs beneath the seabed despite the total destruction going on above them. Which leaves us with this final thought. The next time you see a picture of an offshore platform, remember that the most vital piece of safety equipment isn't the massive steel structure above the waves, and it's not the high-tech control rooms. It's a silent, spring-loaded flap of aerospace metal buried 90 meters beneath the mudline, patiently holding back the immense power of the Earth. When disaster strikes the surface, this hidden savior really is the only thing standing between safety and catastrophe. Thanks for joining me for this explainer, and I'll catch you in the next one.